2 meters long. And I'm going to do a cross section here. 10 millimeters wide. So the area is pi 10 millimeters squared over 4. And if we want to convert that in 2 meters, divide by 1,000 squared. Pi 10 squared over 4. 78.5 millimeters squared. Or a very small number. 0, 0, 0, 0. 785. 4. Since there's a 9 there, I'm definitely going to keep that rounded. This is in meters squared. So 4 zeros. Converting to meters is kind of funny. All right. And then it's in tension, right? So I like drawing little arrows to remind myself that. And so if it's under tension, it's going to elongate. And if it's under compression, it's going to squish back down. So stress. Okay, Hooke's law. They gave us elasticity, and they said 210 gigapascals, which is huge. We don't know epsilon, but we do know sigma, and that is 12 kilonewtons divided by our area. So kilonewton over meter squared. A pascal is a newton meter squared, so this is a kilopascal. That's the unit over here. You have to be super careful what unit you're using. 7854. So we're at 152.8 kilopascals, and oh, whoops. A whole factor of 1,000 off. I'm at 1,502, 788 kilopascal. Sorry. Jeez. I was just saying how you have to be careful of your units, and I messed one up. And then 152.8 megapascal. And I guess they said your ultimate strength is 200, and they wanted you to think about, is this number less than that number? And since it is, I guess we're okay, since we didn't hit our limit. So 152.8 megapascals is equal to 210 gigapascal. I'm going to go ahead and make it megapascal. And then our epsilon, sorry, I'm doing this Hooke's law again. our epsilon is actually change in length over original length. And they want to know, and we know our original length. So our original length was 2 meters. And then we have 152.8 megapascals and megapascals. So you can kind of see that our change in length ratio here is going to be here. I kind of want to make a side note. 152.8 megapascal divided by 210,000. So this is the proportionality to the change in length over the original length. So like a factor of 1,000. So intuitively, based on how stiff this material is and how much load there is, we're talking 2,000ths of a meter. So like somewhere in this range. So like that would be my guess of what we should be seeing, something like 10, 100,000. So this 2 is multiplied by that ratio to actually get the fleshed out number, 52.8. Okay, and I like looking at my zeros in the front. Okay, so I've got 001455. And this is going to be meters. Which if you want, you can multiply that by 1,000, move the decimal, 1.455 millimeter. So that's observable. If you were to look at that, you would see something move. All right. So that's strain and example 1. I think I want to go do more examples of strain.